When we picture the quantum computing revolution, we usually imagine like a sleek, glowing microchip.
Right, yeah. A perfectly tidy, self-contained little box of the future.
Exactly. We don't picture trying to cram 1 million thick, wideband coaxial cables into a freezer.
A freezer that has to be kept significantly colder than the vacuum of deep space, I might add.
Yeah, colder than deep space.
Yeah.
But as we look through the stack of research and reports we've pulled together for you today, that messy, frozen nightmare is exactly what's standing between us and the future.
It really is.
Because it is March 23, 2026, and we have officially reached what scientists in these papers are calling the transistor moment of quantum computing.
Which is a phenomenal yet, incredibly chaotic milestone. And it's why jumping into this deep dive right now is so essential.
Definitely.
Because if you look at the foundational physics of quantum computing, that puzzle is largely solved.
Right. We have functional multi-hundred qubit systems available on the cloud today.
We do. But the goal isn't just to run noisy intermediate experiments. The goal is utility scale machines. Quantum computers capable of trillions of reliable operations or teraquops that can solve commercially relevant problems.
The real world stuff.
Exactly. And to get there, we are no longer fighting a battle of theoretical physics. We are fighting a monumental engineering crisis.
Okay, let's unpack this. Because the mission for our deep dive today is to cut through all the dense academic jargon for you and get straight to the real aha moments about what's actually holding up this revolution. We are facing what the reports call the tyranny of numbers. If you want to solve real-world problems, you need millions of qubits.
Right.
But scaling up a quantum computer isn't like scaling up a traditional server farm where you just, stack more racks in a room. We're looking at 4 interlocking, massive physical barriers.
Yeah, and if we connect this to the bigger picture, you have to understand that these 4 barriers, the physical hardware wiring, the atomic materials, the real-time error correction, and the synthesis of the algorithms, they all have to be breached simultaneously.
You can't just solve 3 out of 4.
No, not at all. If even one of these pillars fails, the delicate quantum state collapses, and your multi-million-dollar calculation just turns into random noise.
Wow. Well, let's start with the most immediate physical roadblock. The cryogenic bottleneck.
The freezer problem.
The freezer problem.
Yeah.
Because you can't use a million-qubit quantum computer if you literally can't plug it in without melting it.
Right.
To protect these incredibly delicate superconducting qubits from environmental thermal noise, basically the ambient heat of the universe, you have to isolate them at the very bottom stage of a dilution refrigerator.
And that stage operates at 10 millikelvin.
10 millikelvin.
Yeah, to put that in perspective, that is just a fraction of a degree above absolute zero.
It's wild.
And here is where that tyranny of numbers hits you like a brick wall. In contemporary brute force architectures, every single qubit needs its own individual control and readout line.
Running all the way from that freezing base stage up and out to room temperature electronics.
Exactly.
It's like trying to wire up a million high-end home entertainment systems with millions of thick cables all crammed inside a freezer that fundamentally cannot absorb any heat.
The physical space required for that cabling alone exceeds the volume of the fridge.
Right. But more importantly, the heat those cables naturally carry from the outside world destroys the qubits.
It does.
So if the wires in the space are the problem, why can't we just build a bigger freezer to fit them all or use AI to control the heat?
Well, a bigger fridge doesn't solve the laws of thermodynamics.
Unfortunate but true.
Right. The issue isn't just ambient air temperature, it's thermal electromagnetic radiation. If you dissipate even a microscopic amount of heat at that 10 millikelvin stage, that energy radiates outward as photons.
And those photons hit the superconducting qubits.
Exactly. They knock them out of their quantum state and cause fatal computation errors. The cooling budget we are working with at that bottom stage is incredibly strict. It is less than or equal to 20 microwatts.
Wait, 20 microwatts?
Yes, 20 microwatts.
That is basically nothing. Like a standard LED light bulb uses millions of times more power than that.
It is practically zero. So the entire industry is pivoting toward cryogenic multiplexers.
Which are what, exactly?
They're switches that sit inside the fridge, allowing you to route multiple signals through just a few wires going outside.
Real clever.
It is. But the current tech is hitting a wall. We've tried cryo-CMOS switches, which use standard transistor technology modified for the cold.
But pushing electrons through a semiconductor inherently creates resistance
Right.
and leaks energy.
Exactly. They suffer from 1.6 to 2.5 decibels of insertion loss, which degrades the signal-to-noise ratio way too much. The signal gets too quiet, and the noise gets too loud.
And reports say we also tried high electron mobility transistors, or HEMMTs, right?
Yeah, HEMMTs. But those introduce even more loss, around 5 decibels. Plus, they use materials that just don't play nicely with standard chip manufacturing.
Which brings us to MEMS, microelectromechanical systems.
Yes, MEMS are currently our best hope for staying under that 20 microwatt limit.
Because unlike a traditional transistor that pushes electrons through a channel, a MEMS device is a literal microscopic physical machine.
Right. It acts like a tiny mechanical drawbridge that physically opens and closes to route the signal.
That's amazing.
And because it creates a physical gap when open, it drastically cuts down on that thermal and electrical leakage.
So we're building microscopic mechanical drawbridges to keep the freezer cold.
Basically.
But even with perfect drawbridges, there's still heat fluctuation. Going back to my earlier point, can we use AI to somehow manage the cooling system and magically freeze the heat?
Well, AI cannot break the laws of physics to generate more cooling power.
Fair enough.
However, it is being used to manage the fight-out of those thermal realities. Researchers are taking classical FPGA hardware very fast, programmable chips, and running AI on them right next to the fridge.
Oh, I see.
Yeah, this AI tracks sudden fluctuations in qubit performance, like relaxation rates, about 100 times faster than old methods.
So instead of like a lifeguard jumping in to pull a drowning qubit out of the heat, it's more like an active suspension system on a high-speed race car.
That's a great way to visualize it.
The AI is reading the road and adjusting the shocks in fractions of a millisecond, recalibrating the system before the chassis even feels the bump.
Yes, it's an active, real-time triage system, identifying when a qubit flips from a good state to a bad state, and adjusting the calculation on the fly before the error ruins everything.
Wow. But let's say we actually solve this wiring crisis. Let's say we build the perfect micromechanical drawbridges and the freezer stays perfectly cold.
Clear.
We are still hitting a wall because the qubits inside that freezer are just fundamentally too fragile. We're essentially building the perfect machine out of the wrong raw materials.
This is a massive shift in the field right now. For a long time, we relied heavily on mapped organic molecules.
Right.
But functional inorganic quantum materials, the raw atomic structures you actually need to host a highly stable qubit, they're incredibly scarce in nature.
Because the quantum phenomena we rely on are tied to very specific, highly complex geometric patterns at the atomic level, right? Like honeycomb or Kagome lattices.
Exactly, and humans are just too slow at discovering these in a lab. So we've handed the keys over to generative AI.
But we're not talking about a chatbot here.
No, we are talking about frameworks like SCIGEN.
SCIGEN, right.
Yeah, this uses diffusion-based generative models to design brand new inorganic materials entirely from scratch.
But to make sure the AI isn't just hallucinating impossible magic rocks, every generated material is forced through a brutal 4-stage mathematical pre-screening process.
It's a fascinating gauntlet. First, charge neutrality. The material has to balance out electrically.
Makes sense.
Second, the space occupancy ratio must be tightly constrained.
Right. The reports mention it has to be less than or equal to 1.7.
Yes.
But what that actually means for you listening is that the AI has to be mathematically stopped from just clumping all the atoms together into a useless, dense ball. It forces the AI to build elegant, spacious atomic scaffolding.
Precisely the point. You need that specific geometry for quantum states to survive.
Okay, what's the third stage?
Third, and this is the big one, is thermodynamic stability. The system uses Euclidean neural networks to predict something called the energy above the convex hull, or E-hull.
Think of the convex hull like a topographical map of valleys and mountains. The AI is calculating if this new invented material will rest stably down in a valley,
Right.
or if it's perched precariously on a mountain peak where the second you try to manufacture it in the real world, it will instantly degrade and fall apart.
Exactly. And then the fourth stage ensures structural distinction, making sure it's actually a pristine new structure and not just a noisy, useless variation of a material we already know about.
Here's where it gets really interesting, though. In traditional chemistry, AI models notoriously hit what's called a generalization barrier.
You do?
It's like an AI that has only ever been fed recipes for baking bread, and suddenly we are asking it to invent a blueprint for a nuclear reactor. It usually has no idea how to jump to an entirely new space.
Right.
Wait, if traditional models hit a generalization barrier in new chemical spaces, why should we trust this AI? Why can't we just test these structures in a physical lab?
Well, because waiting for the physical lab cycle would take decades we don't have. The reason this new wave of AI breaks that generalization barrier is through closed-loop synthesis.
Meaning it learns from its own failures.
Exactly. It doesn't just guess and move on. The generative models are coupled with iterative retraining on high-throughput density functional theory simulations.
So the AI proposes a new material, a massive classical simulation, tests the physics of that material, tells the AI exactly where and why it failed, and the AI immediately rewires its own understanding.
This active learning approach is the game changer. It has reduced property prediction errors by 19 times.
19 times.
Yeah. The precision of identifying a truly viable top material candidate jumped from a dismal 7% to 86%.
That is a massive leap.
And crucially, it is the only demonstrated method that consistently advances what we call the known Pareto front.
Meaning it's actively finding optimal combinations of properties like stability and quantum coherence that do not exist in any current human database.
It generates stable, synthesizable structures 3.5 times faster than traditional static models. By letting AI map the uncharted territory of physics, we are projecting a 10 to 20 times reduction in R&D cycles.
All right, so let's say our miracle MEM switches are working, and our AI invents a flawless inorganic Kagome. We build the processor. But we still live in a universe full of ambient radiation and tiny magnetic shifts. Environmental noise still seeps in. Once you build the hardware, how do you stop the software from crumbling under physical error rates?
This is the defining technical challenge for reaching quantum utility. Right now, physical error rates are generally between 1 in 1,000 and 1 in 10,000 per gate operation.
That might sound low to some people.
It might, but in a complex algorithm requiring millions of sequential steps, that error compounds exponentially. It strictly limits how long you can run a computation before your result turns into garbage.
To reach that teraquops milestone, trillions of reliable operations by the 2028 to 2030 window, we need decoders that can identify and fix errors in real time.
We do.
But the hurdle is the sheer speed of the quantum system. The error avalanche happens so fast that these decoders have to operate at sub-microsecond speeds, specifically under 480 nanoseconds.
This is where AI steps in yet again, this time within quantum error correction. We're seeing the implementation of AI-based systems like the local clustering decoder, or LCD.
LCD, got it.
They offer significantly lower latency, meaning they process the data faster and better accuracy for specific error models than our traditional algorithmic decoders.
But the AI isn't just slapping band-aids on the errors, right? It's actively rewriting the algorithms we run.
Yes.
We're talking about automated algorithm synthesis using POMDPs, partially observable Markov decision processes. Let me try an analogy here.
Sure, go ahead.
Imagine a traditional quantum algorithm designed by a human is like a beautiful, intricate piece of sheet music written for a grand piano.
A highly sensitive, very fragile grand piano.
Exactly that. But on a real quantum computer, 3 of the piano keys are broken, the sustain pedal is stuck, and someone is occasionally throwing a tennis ball at the strings.
Right.
A human would just blindly play the sheet music and the song would sound awful. But these POMDPs are like an AI that analyzes the broken piano, realizes exactly which keys don't work, and dynamically rewrites the sheet music on the fly.
Changing chords, shifting melodies to different octaves.
Exactly. So that the final song still sounds perfect, mathematically embracing the broken hardware rather than fighting it.
That is highly accurate. These AI synthesized algorithms are mathematically tailored to the specific, unique noise profiles and physical layouts of the exact machine they are running on.
That's brilliant.
And because of that, they look totally alien compared to human-designed methods. If you look at a human-designed indirect parity measurement algorithm, it is logical, it is highly symmetrical.
But the AI version?
The POMDP output looks like chaotic noise to a human engineer. But to the machine, it is the absolute most efficient path possible.
And while we wait for these flawless systems, the reports mention we are using error suppression to just survive the current noisy intermediate scale quantum era.
Right, the NISQ era.
Yeah.
Things like dynamical decoupling, which literally just fires random pulses into the qubits during their idle time to constantly distract them from absorbing environmental noise.
Oh, and measurement error mitigation, or MEM.
Yes. It's all about buying us time and computation depth until we reach true fault tolerance.
Which opens up a fascinating question. Everything we've talked about so far is the standard roadmap to a massive, fault-tolerant quantum computer. But what if we don't want to build a warehouse-sized freezer with 1,000,000 qubits? What if there are shortcuts?
That's where the field is diverging in some incredibly disruptive ways. Researchers aren't just putting all their faith in superconducting qubits.
What else are they looking at?
For instance, to bridge the gap between noisy machines and fault-tolerant ones, they're using Krylov quantum diagonalization, or KQD. It recently ran on 56 qubits.
Okay, how does that work?
Rather than running a long, drawn-out calculation that gives the noise time to ruin the answer, KQD mathematically takes a shallow exponential shortcut, finishing the computation before the environment can destabilize it.
Outrunning the noise.
Exactly. We are also seeing density quantum neural networks acting as a mixture of experts.
Let's break that down. A mixture of experts essentially means that instead of activating the entire massive neural network for every single problem, which draws huge amounts of power and invites more noise, the system acts like a triage nurse.
Right.
It routes specific types of problems only to the specific small clusters of the network best equipped to handle them. It is vastly more efficient on hardware that has limited depth.
And on the hardware side itself, we're seeing breakthroughs in semiconductor exchange-only architectures.
Oh yeah, using standard 300mm semiconductor manufacturing.
Exactly. The exact same fabrication plants that make the classical chips in your smartphone right now. They're using them to run complex gate operations in a maximally parallel way, reducing duration by 40%.
So if you can leverage existing global manufacturing infrastructure, scaling to millions of qubits becomes a standard industrial process rather than a bespoke, custom laboratory experiment.
Precisely.
But perhaps the most mind-bending alternative path is the trapped ion architecture. Systems like the Quantinuum H11.
Yes.
Unlike superconducting qubits, which we have to manufacture and are prone to microscopic defects, trapped ion qubits are just individual atoms. Nature already built them flawlessly.
They are naturally identical.
And they boast world record gate fidelities of 99.99%.
Yeah.
And they allow every qubit to connect to every other qubit. Plus, they have on-chip verification up to 52 vertices. So if trapped ions give us 99.99% fidelity and are completely naturally identical, why are we bothering with anything else? Why isn't that just the undisputed winner?
What's fascinating here is that perfection at the micro level creates massive complexities at the macro level.
So,
Well, yes, a single trapped ion is perfect,
yeah.
but you cannot physically cram 1,000,000 atoms into a single trap.
Oh, because they interact.
Right. The atoms begin to repel each other, the control lasers required to manipulate them get exponentially too complex, and the whole system destabilizes. Scaling trapped ions requires linking many small modular units together via photonic interconnects. It's called distributed quantum computing, or DQC.
So instead of building one giant brain, it's thousands of smaller, perfect brains trying to work together over a network.
Exactly. And coordinating those separate processors without introducing massive delays and noise from classic communication channels is incredibly difficult.
Which brings us to...
This is where we encounter the phenomenon of quantum pseudo-telepathy.
I love that phrase, quantum telepathy.
It sounds like pure science fiction, but it is a rigorously proven mathematical protocol. It uses quantum entanglement and the violation of Bell inequalities to achieve non-local coordination.
So it allows separate parts of the distributed computer to synchronize their decisions instantaneously.
Yes, and verify benchmarks without ever sending classical noisy signals back and forth. In 2026, experiments on these systems achieved win rates in coordination games exceeding 95%.
That's incredible.
It is the necessary foundation if we want a modular quantum future.
We've covered a staggering amount of ground, but there is one overarching irony to all of this.
Oh, what's that?
To build, design, verify, and run these mind-bending quantum systems, we are utterly reliant on the absolute pinnacle of classical computing. We literally cannot reach the quantum future without maxing out the biggest classical supercomputers on Earth today.
It's a deeply symbiotic relationship.
Tell me about the Jupiter project.
Right, take the Jupiter Supercomputer's JUQCS50 project. Recently, they successfully simulated a 50-qubit universal quantum computer.
Right.
To do that, the classical supercomputer had to track 2 quadrillion complex numerical values just to simulate a single quantum gate operation.
2 quadrillion.
And that was with an 8 times reduced memory footprint.
2 quadrillion values just to simulate the behavior of 50 atoms. That is staggering. And systems like Frontier and Aurora are simulating the quantum many-body problem, right?
Yes, tracking the behavior of up to 17,000 atoms using codes like Berkeley GW, just to provide the physical calibration data that the AI needs to discover the materials we talked about earlier.
But wait, if a classical supercomputer can simulate 50 qubits, and classical AI is running the error correction, aren't we just building a really expensive classical computer with a quantum accessory?
It can absolutely look that way, but the exascale systems are the scaffolding, not the final building. We need them right now for verification.
Just check the math.
Right. When a quantum computer solves a vastly complex problem, how do you know the answer is right if a classical computer can't solve it to check the work?
Good point.
The exascale systems provide the classical hardness verification. They push classical algorithms to their absolute mathematical limits to prove exactly when and where the quantum systems finally eclipse them, achieving true quantum advantage.
So it's hybrid integration.
Exactly. Ultimately, this co-design creates a hybrid quantum-centric supercomputer where each processor handles exactly what it does best.
So what does this all mean for you listening right now? The journey from a tidy physics experiment to the messy transistor moment of 2026 is brutal.
Very much so.
To bridge that gap, we have to solve the cryogenic wiring crisis with tiny mechanical drawbridges, the MEMS. We have to design never-before-seen inorganic scaffolding using SCIGEN and active learning AI.
Right.
We have to manage the avalanche of physical noise with sub-480 nanosecond AI decoders. And we have to completely rethink our software using POMDPs that dynamically rewrite algorithms on the fly.
It is a multifaceted engineering war.
So the next time you hear a headline making massive promises about a quantum breakthrough, you now know to look past the hype. You know the actual right questions to ask. Did they fix the wires? Did they actually discover more stable material? Did they beat the error avalanche?
And as we wrap up, I want to leave you with one final thought based on the source material, something I haven't touched on yet.
Oh, what's that?
We've spent a lot of time talking about massive deep space dilution refrigerators and exascale supercomputers working in tandem.
Yeah.
But hidden in the material discovery research is the development of something called topological chiral electronics.
Right, the chiral fermionic valves.
Exactly. By using quantum geometry to filter fermions, the fundamental particles carrying the electrical current researchers can filter them by their chirality or their spin direction.
Okay, what does that look like in practice?
Think of it like a VIP lane on a highway where all the cars are perfectly synchronized so no one ever crashes. Because the particles don't crash, there is no resistance and therefore no heat.
Wow.
They've achieved phase-coherent transport over distances greater than 15 micrometers without needing massive magnetic fields.
Which means?
What this means, practically, is the ability to use quantum phenomena to build ultra-low-power electronics at room temperature.
At room temperature.
Yes. So while we are fixated on building these giant freezing quantum supercomputers, perhaps the true endgame of quantum computing isn't just a massive server farm.
What else could it be?
Perhaps the endgame is that we master these quantum materials so completely that quantum mechanics fundamentally redesigns the everyday room temperature electronics sitting in your pocket right now.
From a million cables crammed into a deep space freezer to a zero-resistance quantum-powered phone in your pocket. That is a wild trajectory. Thank you so much for joining us on this deep dive. Keep questioning the architecture of the future, and we'll see you next time.